Okay, so welcome everyone to today's Foxconn Quantum Computing Seminar. And today we have the pleasure of having Kieran Mastel for our seminar talk for today. So Kieran is a PhD student in pure math at the University of Waterloo. I guess you're also affiliated with IQC, right?
Yep, that's right.
Yeah, and your supervisor is William Slofstra. Yeah, and he works mainly on non-local games and the application of representation theory in quantum information. And in his personal bio, he also says that he is an avid rock climber. Seems to be the sort of thing that physics people like to do. I know lots of people who do this. Yeah. Uh, okay, so yeah, the floor is yours.
All right, right on. Thank you.
Mhm.
Yeah, so thanks very much for the invitation to speak today. So yeah, I'm going to talk about some work that I've been doing with my supervisor, William Slofstra, on two-prover perfect zero knowledge proofs for MIP star. So the intuition of a multiprover interactive proof is that two computationally unbounded provers, Alice and Bob, want to prove that a string X is in a language L to a polynomial time verifier. And the players can strategize together before the game begins, but they're not allowed to communicate during the game. An MIP protocol is a sequence of games indexed by strings X, such that if X is in the language, then the players have a strategy that they can employ such that they win with probability 1. And if X is not in the language, then the players, no matter what strategy they employ, can win with probability at most S, which is called the soundness parameter. So an example of this type of scenario is the graph coloring game, where Alice and Bob want to convince the verifier that they know a 3 coloring of a given graph G. And here, the verifier's questions, I and J, are vertices, and Alice and Bob's responses, A and B, are colors. If they're asked for the same vertex, they must respond with the same color. And if they're asked for adjacent vertices, they must respond with different colors in order to win. And here it's clear that that Alice and Bob only have a perfect strategy if there is actually a 3 coloring of the graph that they're asked to play the game for. And so we denote by MIP the class of languages with multiprover interactive proof systems where the provers have access to classical resources such as shared randomness. We can also imagine, so here I've only drawn 2 provers and one round of interaction where the verifier is asking a question of each prover, receiving an answer from each prover. But we can imagine having more provers than just 2, and we can imagine having more rounds than just 1. We can imagine the verifier asking multiple questions and receiving multiple answers in succession, for example. But I emphasize the classical resources at the end of this part of the slide here, because if we live in a quantum mechanical universe, then Alice and Bob can share a quantum state. They can share some entanglement. So here they share a state psi that's in the tensor product Hilbert space. And upon receiving her question I from the verifier, Alice is going to perform a positive operator valued measure to get her answer A. And Bob's going to similarly condition his response on a POVM. And then the probability that they answer AB on question pair IJ is just the expectation value of the tensor product of their measurements. The collection of measurement operators and the state that they share together is called a strategy for the players. So that's the freedom they have in determining how they're going to respond to any given question pair. That's the strategizing that they can do before the game begins. And an example of how this gives the provers more power is that there are graphs with no 3 coloring, but for which the provers can play the 3 coloring game perfectly if they share some entanglement. And then MIP star denotes the languages with multiprover interactive proof systems where the provers can share some entanglement. So on the previous slide, I emphasized that the provers share state in a tensor product Hilbert space. But there are other possible models of entanglement. So in order to talk about models of entanglement, we talk about the correlations that the provers can produce with that entanglement as a resource. So the probability distribution conditioned on the question pairs is called the correlation that the players can produce. And a correlation is quantum if it can be produced by a scenario like the one on the previous slide, where the players share a state in a tensor product Hilbert space. Their measurements are POVMs on each factor of the Hilbert space, and then the correlation is just an expectation value of their POVMs. But we can imagine a scenario where instead of having a tensor product of two Hilbert spaces, one for Alice and one for Bob, we have just one big Hilbert space, and the only condition on Alice and Bob's measurements is that they have to commute with one another. They have to be simultaneously measurable for any question pair that's asked. And this is called commuting operator entanglement. And it's a potentially bigger class than the quantum correlations. And then we denote by CQA the closure of the set of quantum correlations. So anything that can be achieved as a limit of any correlation that can be achieved as a limit of these types of strategies, these tensor product strategies. And then we have this list of strict containments. The quantum correlations are not closed, so they're strictly contained in CQA, and CQA is strictly contained in the commuting operator correlations. So now,
sorry,
yes,
can I interrupt?
Yes,
is
you
it
may.
easy to see that it's not closed?
So no, it's not easy to see that it's not closed. This was the subject of my supervisor, William Slofstra, one of his big papers, I think, in 2019. He showed that the set of quantum correlations is not closed by constructing a family of non-local games whose limiting correlation was not quantum. So yeah, a family of MIP star scenarios, all of whom have commuting operator style, or not commuting operator, sorry, tensor product style, quantum style entanglement that gives perfect strategies, but for whom the game in the limit, as n goes to infinity for that family of games, does have a perfect strategy in potentially a commuting operator model, but doesn't have a perfect strategy here.
Okay.
Does that make sense?
I feel like I vaguely heard about this result, so kind of makes sense.
Uh-huh.
Although I mean, I guess like I don't fully remember how it's shown. I guess I was just wondering like whether it had to do with like having to use infinite dimensions in one case or the other, but I guess it's irrelevant, right?
Yeah, so right. You do have to take the limit as the dimension of the Hilbert space goes to infinity for sure. It does rely on infinite dimensional Hilbert spaces. In finite dimensions, these models are the same.
Yeah. I guess like it's sort of like because I almost all exclusively work in finite dimensions. So when I see this, wait, these look the same in most cases.
Right. Yeah. So in that case, you're right. Yeah. In finite dimensions, it's all of these models end up being the same thing. It's only in infinite dimensions when you start to see the difference.
Okay. Yeah. Sorry for the interruption.
Hey, no worries. It was a good question.
I just want to
wait. I think someone. Yeah. Sure.
I just want to clarify. So CQ, ACQ, these guys, they are kind of some certain strategy or correlation between the prover? Or I mean, or what's the classification?
Yeah, so the sets CQ and CQC and CQA are just all sets of correlations that the provers can achieve between their answers.
Okay. And Q and QC, what's the difference? Sorry.
So the difference between Q and QC is that in quantum, in CQ, the Hilbert spaces are tensor products, right? They have a state that's in a tensor product of HA and HB, and then they achieve their correlation this way by measuring their POVMs on each tensor factor. But CQC correlations have only one Hilbert space, and then the prover's measurements are POVMs that commute with one another on that single Hilbert space.
Okay, I see. Thank you.
Yep. Okay. Moving on to the second half of the title, the intuition for perfect zero knowledge is that Alice and Bob want to prove that a string X is in a language L to a referee without revealing any other information than the fact that the string is in the language. So what do we mean by without revealing any other information? Well, when the verifier interacts with Alice and Bob in an MIP star scenario, all they see is the probability distribution PABIJ, the correlation generated by their answers in response to any question pair. And we say that a MIP star protocol is perfect zero knowledge if there's a polynomial time Turing machine S, which we call the simulator, that can output the exact same correlation, PABIJ, and such that the correlation that the simulator outputs, PABIJ, is a quantum correlation that is the players can instantiate it using a quantum strategy, like on the previous slide, if X is in the language. And so the idea there is that if we're in an accept instance, if X is indeed in the language, then the verifier can pre-compute, because the verifier is a polynomial time Turing machine, the verifier can pre-compute the correlation they expect to see if the provers actually can demonstrate that X is in the language. So the idea is they're not surprised at all by the correlation they see in an accept instance. So there's been a lot of...
sorry, another question.
Yeah, no worries.
The simulator... Doesn't the simulator need like the psi as an input? Or
so no,
it needs to get something, right?
So the simulator doesn't need psi as an input. The simulator takes X as an input, though.
Oh, X is the only thing that it needs?
Yeah, X is the only thing that it needs. The idea is that the simulator doesn't have to simulate Alice and Bob separately, right? Because it's just one Turing machine.
Okay.
Yeah, so it has access to both questions, but Alice is only going to have access to her question I, and Bob's only going to have access to his question J. And so that's the advantage of the simulator. That's why we can hope to
and I guess the simulator only needs to sort of reproduce the correlation, not
that's
the
right.
round by round result.
Yeah. Yeah, exactly.
Yeah.
Okay.
Sorry, what does the X refer to here?
So S, it's just a polynomial time Turing machine that
X.
given the input X can, the string, you mean, the string X.
Yes.
Yeah, so this is just like a computer science decision problem. We have a language L, and we want to know if the string X is a member of that language.
I see, but in the setting, like the nonlocal game setting, where is the X?
Sorry, in the
tool setting, where does the X come in?
I guess they're asking like in the left figure, or I guess like maybe below. Like, okay, so the simulator will get X as an input, right? So in the
Yes, yeah.
non-local game, where is the X?
Ah, right. Okay. Where is the X? So, for example, think of the graph coloring game. There, the string X is like a description of the graph, and you're asking, is that graph three colorable? So the language is all three colorable graphs. And so here, like X is part of the particular instance that the players and the verifier are agreeing to play. So like before they begin playing the game, the verifier will say, okay, I'm going to be asking questions about this graph. And everybody knows the input that they're taking, the graph that they're taking as the input for the game.
Okay, I see. That's clear. Thank you.
Okay, great. All right. So there's been a lot of really great work on perfect zero knowledge for both MIP and MIP star. It was known at the inception of MIP as a complexity class that every language in MIP admits perfect zero knowledge protocol. And Babai, Fortnow, and Lund famously showed that MIP with two provers and one round of interaction is equal to NEXP, and also is enough to capture the entire complexity class. Then after the introduction of MIP star in 2018, Chiesa, Forbes, Gurr, and Spooner showed that all of NEXP, so all of MIP, is contained in perfect zero knowledge MIP star with two players and polynomially many rounds of interaction. So every MIP, every classical MIP admits a perfect zero knowledge quantum MIP. Then in 2019, Grilo, Slofstra, and Yuen showed that perfect zero knowledge MIP star with four provers and only one round of interaction is enough to capture the whole class. And stunningly in 2020, Natarajan, Vidick, Wright, and Yuen showed that two provers and one round is enough to capture the entire complexity class of MIP star, and it's also stunningly equal to RE. So the difference between 4 and 2 here prompts the question, can we bring perfect zero knowledge MIP star down to two provers like we can in the classical setting? And the answer in this work is yes. That's our main result. We show that there's a two prover, one round, perfect zero knowledge MIP star protocol for all of MIP star. So one way you might go about thinking to prove this result is by trying to improve the techniques of Grilo, Slofstra, and Yuen from 2019. They use a strategy called simulatable codes, where they take the state that the provers share, and they encode it in a quantum error correcting code, and distribute it amongst the provers, so that sort of each prover's view of the state is evenly distributed in some statistical sense. But their data hiding argument that works with four provers seems difficult to apply in the context of two provers. So instead, we specialize to a type of game called Boolean constraint system game. So I'll just quickly introduce what I mean by a Boolean constraint system. It's a pair X and VI-CI, where X is a set of variables and VI is a non-empty subset of X for all I 1 up to M. And CI is some constraint on the variables VI. And then the sets VI are sometimes called the context of the system. And a satisfying assignment for the BCSB is just an assignment to the variables in X such that the restriction to each context is allowable for the constraint on those variables for all I. And then a BCS game is a scenario where B is a BCS and the players are asked for indices of constraints in that BCS, and they must respond with satisfying assignments to the constraints that they've been asked for. And they win if their satisfying assignments agree on the variables in the overlap of their contexts. And an advantage of BCS games is that we can work with assignments to the variables rather than with arbitrary strategies of the players. Because sometimes in MIP Star, it's hard to pin down what strategies the players can employ and what they should employ. Another advantage is that they allow us to use what are called Kilian randomizing tableau. But before I get to the tableau, there's a transformation we do on BCSs before we apply that, called obliviation, where we take a constraint in a Boolean constraint system, and we replace each variable with the XOR of 5 new variables, which we call the oblivious variables. And an important idea for obliviation is that in order to recover the value of one of the original variables in the original BCS, you need the value of all 5 of the new oblivious variables. So if you have up to 4 of them, you don't learn anything about the value of the original x from, say, x1 up to x4. So then Kilian randomizing tableau is a way of allowing the provers to demonstrate to the verifier that they hold the satisfying assignment to a BCS, but restricting the verifier to learning only low moments of the player's assignment to those variables. So the idea is we take some variables x1 up to xd and use what's called a permutation branching program to transform the assignment to x1 up to xd into a permutation valued variables, pi1 up to pi d, in such a way that the product of the permutation valued variables, pi1 up to pi d, is equal to some 5-cycle sigma if the original assignment satisfies the original constraint, and is equal to the identity otherwise. So here, pi1 up to pi d are permutations in S5. And then we generate each subsequent,
Yeah, sorry. I'm just curious, like, because you replaced the variable with like 5, is there any like intuition why 5 was needed?
Right. Okay. So the intuition for why 5 is needed is that when we allow the verifier to perform the consistency checks on this tableau, they're going to learn up to 4 values of these oblivious variables at the top here. So of these original assignments up here. And so in order to make sure that those can be uniformly distributed and therefore sampleable by a polynomial time simulator, we do this obliviation up to 5. So it's just 1 more than the maximum number that the verifier can learn by asking the players questions.
And the 4 that the maximum that the verifier can learn is, so that's the max for any situation.
Yeah, for any question pair. Yeah. So there are scenarios where the verifier is going to learn less values of these top row x's, but
and then of course, like 5 is good enough. You could have 5 but
yeah, we could have more, and it would be like somehow more secure in that way, but we don't need any more in order to get the perfect zero knowledge.
Okay.
Yeah. And so we construct each subsequent row of the tableau by multiplying the element directly above it on the left and right by uniformly randomly selected elements of S5, so uniformly randomly selected permutations, in such a way that the product of each row remains the same. So in particular, the product of the elements of the fourth row will be equal to sigma if X is satisfying, and will be equal to the identity otherwise. And how we prevent the verifier from learning more than 4 of these original XIs is by restricting the verifier to only checking that the product of the fourth row of the tableau is correct, and also checking that each element of the tableau was constructed correctly from the element directly above it. So any more questions about this?
We'll give more information, I guess.
Sorry?
I mean, like, so you were saying that you're only asking for a certain row, right? Like the last row?
Yeah. So
Like,
the verifier
you're only asking for a certain structure of the tableau, right?
Yes.
Because I guess otherwise, if you allow them to ask for every part of the tableau, then they would be able to know everything.
Yeah, exactly. So if the verifier could ask for, you know, an arbitrary size chunk of the tableau and then check the consistency of that, then that wouldn't give us perfect zero knowledge, because they'd be able to get arbitrarily many of these top row X's, and then they could reconstruct the verifier's assignment to the original non-oblivious Boolean constraint system that we took as input.
Okay. Yeah. Okay. Yeah. Okay. Sorry for interrupting again.
No worries. It's a good question. Okay. I'll move on. So Dwork, Feige, Kilian, Naor, and Safra in 1992 used this type of construction to show that there's a 2-prover, 1-round perfect zero knowledge proof system for 3SAT. They needed only 3 rows of the tableau and less obliviation, so they obliviate to 3 oblivious variables, but we need 5. And a key insight there is that to use the randomizing tableau to generate that first row of the tableau, the permutation branching program actually blows up the length of the circuit exponentially. So we need constant input clause size in our BCS. So that's why Dwork et al. Use 3SAT. MIP star equals RE implies that Boolean constraint system games are universal for MIP star. So we can capture the entire complexity class that way. We can just look at BCS games, and we show that our main result by showing quantum soundness of the Kilian randomizing tableau reduction. So it's really a classical transformation, and then we're showing that applying it doesn't mess with the soundness parameter from the first slide. So how do we prove quantum soundness of classical transformations? Well, we introduce 2 types of maps between BCSs, and we show that we can analyze the quantum soundness of these 2 types of maps. And then we compose these 2 types of maps to get the randomizing tableau transformation. So the first is the easier type of transformation between BCSs. It's called the classical homomorphism. It maps constraint-wise, so constraint to constraint, and it maps satisfying assignments to satisfying assignments, and assignments that disagree on overlapping variables to assignments that disagree on overlapping variables. There are many instances of this in use in the literature already. For example, G's locally commutative reductions. And these types of transformations actually preserve quantum soundness right out of the box. There's not much analysis required. The other type of transformation we call subdivision, and it's more tricky. We have a big constraint in the original BCS, and we split it up into a number of smaller constraints in the target, such that the OR of all the smaller, the AND of all the smaller constraints is equal to, or is logically equivalent to, the original constraint. What makes these transformations harder to analyze in the quantum setting is that the observables no longer need to commute in different contexts. So if we asked a player in a non-local game, in a MIP star scenario, for an assignment to the constraint C, they would have to measure an observable for each of these variables and tell us the value of each one. So in particular, their observable for the variable x1 and the variable x5 would have to commute with one another because they have to simultaneously measure them. However, in the subdivided BCS, the variable x1 and x5 don't appear in the same context all the time. And so if we were to ask one player for, or if we were to ask a player for constraint D1, then they can measure an observable for x1 that wouldn't necessarily have to commute with their observable for x5 if we asked them for constraint D2. But we can overcome this difficulty, and we show that if there's a strategy for the subdivided BCS game that wins with probability 1 minus epsilon, then there must be a strategy for the original game that wins with probability less than or equal to 1 minus polynomial in the input strings, a polynomial in x, times epsilon. And so this is a polynomial drop-off in the soundness parameter, and we can recover a constant soundness by a polynomial amount of parallel repetition. So the reduction then is we start with an arbitrary BCS, which is complete for all of MIP star. By classical homomorphisms and subdivisions, we can get this BCS into a 3-sat form. And then one more classical homomorphism and subdivision allows us to get this 3-sat into the Tableau game form. So how we prove theorems like the one on the subdivision slide is by introducing a new framework for talking about soundness of BCS transformations, which we call weighted algebras. So here it's a pair A mu, where A is an algebra of observables, and mu is a finitely supported weight on that algebra. And the weight allows us to define a quantity called defect, which measures how far strategies are from being perfect. And an advantage of this technique is that it works for different types of quantum strategies. For example, it works for commuting operator strategies in addition to just quantum strategies. And so perfect zero knowledge BCS MIP co to 1 with 2 provers and 1 round of interaction is equal to BCS MIP co with 2 provers and 1 round of interaction by the exact same argument that we use to prove perfect zero knowledge for MIP star, which is only quantum correlations. And if we knew that BCS games are universal for MIP co, then this would give you a perfect zero knowledge result for all of MIP co. In addition, I guess we would need a parallel repetition theorem for MIP co as well. So there's 2 ingredients that we would require to get perfect zero knowledge for all of MIP co. But the same reduction does work, and the same soundness arguments do work. So I'll take you on a little tour of the weighted algebras technique. First, BCS algebras are the things that we're going to be using the weighted algebra framework to analyze. So what are they? Well, we can think of an assignment as an element of the set Z2 to the V, where V is the set of variables that the assignment is an assignment to. And we can represent an assignment as a polynomial in this way. And we usually denote these polynomials as phi v phi. Then given a constraint C on a set of variables V, AVC is just the set of the algebra of all possible constraint polynomials quotiented by the relations that make the non-satisfying constraint polynomials 0. And if B is a BCS, so a set of constraints, then the BCS algebra, AB, is just the free product of all of the constraint algebras A, V, I, C, I for each constraint in the BCS. So I don't know how friendly the audience is with the notion of a tracial state, but it's just a functional on an algebra that captures the idea of expectation value in quantum mechanics, and synchronous commuting operator strategies for BCS games are equivalent to tracial states on the game algebra AB, defined on the previous slide, and synchronous quantum strategies are equivalent to finite dimensional tracial states on the game algebra. So that's states on finite dimensional Hilbert spaces. Then a tracial state on a game algebra of a BCS corresponds to a perfect strategy if and only if, whenever we have the product of two assignment polynomials to two contexts Vi and Vj, if the assignments disagree on the overlap of Vi and Vj, then the trace of that product will be 0. And we also make the stipulation pi ij not equal to 0. So here that means that Vi and Vj are contexts that are asked for by the verifier from the players together at some point in the game. There's some non-zero probability that this question pair will be asked. So as I said, a weighted algebra is a pair where A is an algebra and mu is a weight. And if tau is a tracial state on the algebra, then the defect of that trace is just the weighted sum of the trace norm of everything in the algebra. And the defect measures how far away tau is from being 0 on the ideal generated by the support of the weight. And so if we define our weight to take non-zero value on all of the things that we want to be 0 in our BCS algebra, then the defect will measure how far our traces are from being perfect strategies. So that's the guided tour of the technique of weighted algebras. We keep track of the soundness of these reductions between BCSs just by keeping track of how they affect the defect of the algebra defined in this way.
Okay.
So
I just wanted to ask.
Yes.
For this like weighted BCS algebras. So this is, I mean, just sort of like a general question of like, this is sort of like well-known thing for a long time.
So the idea of a weighted algebra and using it in this way is new to this paper. This is a new technique. Yeah. So BCS algebras is well-trodden ground. People are very familiar with that in the MIP star literature, but the notion of using a weight on an algebra in this way and defining a defect in this way, that's all new to this work.
Okay, I see. Okay, thank you.
So some view to potential future work. I mentioned that these techniques work for the commuting operator model. So if we have commuting operator parallel repetition and we know that BCS games are universal for MIPCO, then that would immediately give us the result for MIPCO as well, that perfect zero knowledge MIPCO with 2 provers and 1 round of interaction is equal to the whole class. Some stuff that I'm working on particularly right now is applying this weighted algebra formalism to show quantum soundness of other BCS reductions. So an example is another student at IQC and I are looking at the hardness of constant gap graph 3 coloring games. it's known that graph 3 coloring games with no soundness gap is enough to capture all of RE, so all of MIP star, and graph coloring games with a certain sized constant gap are actually in P when you allow the player's entanglement. But there's a question of what does the territory between that constant gap and the zero gap case look like? And we think that we can show that that these games are actually RE hard for some different constant gap. So if the gap is large, then graph coloring is in P, and if the gap is small but still constant, then it could be that graph coloring is RE complete. And all of the reductions that I talked about today are with perfect completeness, and it's unclear how to use these techniques to deal with BCS reductions that allow imperfect completeness. So the case where we might have a BCS with a perfect strategy that maps into some BCS without a perfect strategy. And so I'm also working on generalizing these techniques to that setting. Other questions that are interesting to ask is, does the compression techniques that allow the proof of MIP star equals RE, do they preserve perfect zero knowledge? So if we have a perfect zero knowledge game and we compress it, do we get a perfect zero knowledge game out? And I didn't finish this last line, but the question here at the end is, can we use these techniques to say anything about the hardness of linear constraint system games in the quantum setting? So lin MIP star. This is related to some very desirable questions in group theory, like the question of whether or not there's a non-hyperlinear group, which is also enough to say whether there's a non-sophic group. And so it would be very exciting if we could answer the question of the hardness of lin MIP star. And with that, I thank you all for listening, and I hope the talk wasn't zero knowledge.
Okay. Thank you very much for a very interesting talk. I guess I don't know how many people in the audience are actually have the sufficient math background to be able to really follow everything. But hopefully at least people did get something out of it. Anyway, we will have the recording and we can go through some of what you've said after. I mean, because I admittedly I haven't actually finished reading the paper myself. So maybe I would have learned more things if I did.
Okay. Well,
Yeah.
There's a new version of the paper forthcoming with a. I'm writing a background section on all the star algebra stuff that you need to know for it. And so maybe that'll be helpful if you're going through it yourself.
Yeah.
But I'd be happy to answer any other questions you guys have now or offline.
Yes, yeah. So I guess we have time. We definitely have time for questions right now. Okay, maybe I can ask. So this is why in the I think in your first slide when you defined the completeness, so you did need perfect completeness. That's why you used one.
Yes, exactly. So yeah,
right?
so
yeah,
in general,
I was surprised. That doesn't have to be one. So
yeah,
but
you're
actually
absolutely
needed
right.
That.
You're absolutely right. It doesn't have to be one. I just glossed over it. But yes, but for all of the reductions that I talked about today, it is one. And so that's not
if
actually.
If it wasn't one, it's not clear that your reductions will work.
Yeah, if it's not one, then we need to think of a different or we need to think carefully about how to apply the language of weighted algebras to talk about soundness in that case, and to talk about completeness indeed as well.
Mm-hmm. Mhm. Okay, I think there's some question.
Okay, thank you for the very nice talk. Although I also don't have enough background to follow, but probably I ask some basic question in order that
Sure.
I can follow your paper later on. So I'm just curious, what is your like threshold state for? I mean, it is a strategy or is a a, a pair of state that prover A and B can have? So what's the
So in the finite dimensional setting, all the tracial state is it's just psi, and
I see.
it's the functional that we get by taking the expectation value with psi. A tracial state on a star algebra is just like an infinite dimensional generalization of that idea, I guess. It's the sort of algebraic quantum field theory version of this. And so we're just
So
working in full generality there. That's
so
all that's going on.
you are talking about this certain class of state shared by the A and B, right? In some sense.
Yeah. So exactly. We're really talking about like um A and B, they have some algebra of observables that they could be measuring, and then the tracial state is really, yeah, just like can be thought of as the state of the physical system when they do their measurements. And they also have control over that as well.
And why there is some defect of this state, what are you measuring for?
Sorry?
Yeah, you talk about the defect of this
The
tau.
defect, right.
Yeah,
Yeah.
yeah.
So right. Uh, what the defect is um, it's a way of keeping track of if the players are using state tau, and we assign like negative value to, or not negative value. Basically, the players want to pick a state such that the defect is minimized. Right? That we're asking the players to measure with some probability something in the algebra A that is assigned a positive weight by mu, so a non-zero weight, and the players they perform worse if the defect is bigger, is the idea, because with some probability then they're measuring something that's really far away from zero, but the I guess the intuition for why it works this way can be gleaned maybe from here. The idea in the BCS game is that we're asking the players to measure these observables for assignments to the variables in pairs of constraints. And if we ask for VI and VJ, and the players do a measurement and they get outcome phi and psi, but these two things don't agree on the overlap of their contexts, then they lose. And so they want to be playing with a strategy with a state tau that assigns that possibility, that pair of measurements, probability zero, if that makes sense.
So it's kind of some measure of how the overlap of the measure they have on A side and B side.
Yeah. It's a way of measuring like how bad is the player's strategy, like how much probability, how probable are they to have a measurement outcome that loses the game. That's what defect is trying to measure.
I see.
Yeah.
But in the definition of defect, you are choosing specific tau from this curly A, and why in the definition you also have all the small small a summing over all small a from this same state.
Right. Yeah. So right. The weight here, mu, is a fixed thing by the verifier. The verifier is kind of saying, by assigning like a positive weight to some elements of the algebra, they're saying, I don't want to see these things, right? And the state tau is like the player's choice. So the defect of a state, it's a function of the state that the players are using. So the idea that we use defect for is, if I have a transformation like a classical homomorphism, and I have a state on algebra A, and it maps into algebra B, then I can recover a new state on algebra B, and the idea is that we relate the defect of the original state to the defect of the new state, and using that, we can say something about how poorly the players are doing in the new BCS game relative to how they were doing in the original BCS game, or vice versa.
I see. So it's kind of a transformation from the new one and the original one, and tau is the choice of the prover or the player,
Yes.
and mu is a choice of the verifier, or the choice of who?
Yeah, mu is a choice of the verifier. Yeah, it's
I see.
or really it's kind of like a choice of the input string x, like it's the choice, it's a choice of the BCS in some sense, because it's like in the case here, context I and j overlap on some variables, and so we assign some positive weight to all these things that overlap, but don't agree on the overlap. Yeah.
Mm-hmm. Okay, thank you. Sorry, a final small question. In the very beginning, I asked the correlation of CQ and CQC, and what's the CQA for?
So what is CQA for?
Yeah.
Right. So you can think of CQA as like infinite dimensional tensor product entanglement. So you have an infinite dimensional Hilbert space, but it factors as a tensor product somehow. One tensor factor is Alice's, one tensor factor is Bob's. CQ is by its very nature like finite dimensional Hilbert spaces. Yeah, and so the idea of William's paper about the non-closure of quantum correlations is that there are things that you can achieve in the limit here of like dimension increasing to infinity that you can't achieve with finite dimensional entanglement. But you can, of course, because it's the closure of CQ, you can do arbitrarily close to this, right? Mm-hmm. This second strict containment is a result of MIP star equals RE, and it says that infinite dimensional tensor product entanglement is not the same thing as infinite dimensional commuting operator entanglement. And so there are things that you can achieve in this model of entanglement that you can't achieve in this model of entanglement. And there's like an actual measurable separation between these two things. So if the universe is actually a commuting operator entanglement model, then we could potentially hope to measure the violation of some Bell inequality that shows that we have this type of entanglement, because this is stronger. It's a bigger set of correlations that we could achieve.
Yeah. So when you talk about the infinite dimension of tensor product A and B,
Yeah.
you refer to both infinite dimension of A and B or arbitrary combination like finite A, infinite B, or
Yeah,
any
potentially arbitrary combinations of those two. Yeah. So it could be finite A, infinite B, or infinite both of them, or yeah.
I see. Okay, cool. Okay, thank you very much.
Yeah. Thanks for the questions.
It's a nice talk. Thank you.
Thank you.
Yeah. So I don't know if I'm just waiting if there are any other questions from the other audience members. Okay. Because I guess if not, I think yeah, we're sort of like also at the time at the end of the. Yeah. So okay, so let me thank you again for giving this talk. Okay, I will sort of end the recording now. But okay, I can wait a while to see if other people want to ask questions. Okay, I guess no one